Hello everyone, I'm Priyanka Golia and I'm going to talk about Manthan, a data-driven approach for Boolean function synthesis. This is a joint work with Kuldeep Meal and Shubhajit Roy. This work is going to be published in the Conference of Computer-Aided Verification, CAV 2020. Let us start with the introduction of Boolean function synthesis. So let us have a Boolean relation f between variables x and y, where x is a set of n input variables 1 to xn, and y is a set of m output variables y1 to ym. For each yi, our aim is to synthesize a function psi that takes x1 to xn as an input. The bold psi represents a function vector psi1 to psi_m such that if we replace y by psi of x in the relation f, it still holds. That is, for all the valuation of x where f of xy evaluates to true, f of x psi of x should also evaluate to true. In the literature, psi is called Skolem function and the bold psi is called Skolem function vector. The process of deriving psi from a Boolean relation is known as Boolean function synthesis. Our aim here is to synthesize such a function psi. Let us see this through an example. I have set of inputs x as x1 and x2 and set of output y as y1 and y2, and the specification is described here. Our aim here is to synthesize Skolem function corresponding to every output variable. So we want to synthesize psi1 corresponding to y1 and psi2 corresponding to y2. So we have the specification. Let us look into the first clause of the specification. So here we can see that the y1 if and only if x1 or x2. So it is not difficult to see that the corresponding Skolem function psi1 for y1 will be just x1 or x2. Similarly, if we look into the second clause of the specification, we have psi2 as x1 and x2 or y1. We can replace y1 with this corresponding Skolem function x1 or x2, and on simplification we get psi2 as x1. So that's how we can compute the Skolem function. That was not a difficult example to see. Let us look at another example. So we have input variable x1 and x2 and output variable y1, and the specification is nothing but the disjunction of all the variables. We want to compute a Skolem function corresponding to y1. So we can rewrite the specification as negation of x1 or x2 implies y1. Now it is not difficult to see that the corresponding Skolem function for y1 will be the negation of x1 or x2. But the question arises here, is this the only possible Skolem function for y1? And it turns out that for a particular specification, there can exist multiple possible Skolem function. For example, for this particular specification, we can have negation of x1 or x2 as a Skolem function. It can be negation of x1, negation of x2, or just a constant 1. So for a particular specification, we can have multiple possible Skolem functions, and our aim is here to synthesize one such possible function. Let us move to the application of Boolean function synthesis. It has application in the wide variety of domain. For example, certified QBF solving, program synthesis, cryptography. We will discuss cryptography in detail. The security of well-known encryption algorithm, RSA, depends on the factorization. So the factorization problem is, given a number x, find y such that y is a non-trivial factor of x. So we have an input x and we want to compute the output y, which is a factor of x. It is easy to write the factorization problem as a relation between input and output variable. So we have f between x and y, such that y divides the x and y should not be the part of 1 and x as it is a non-trivial factor of x. Here z represents a set of integers. So now we have a Boolean relation f and we want to compute a function psi that takes x as an input and gives us y, such that if we can replace y by psi of x, the relation f still holds true, and that we can do with the help of Boolean function synthesis. So that's how we can solve the factorization problem using Boolean function synthesis. The objective of this talk is to know the techniques to do the Boolean function synthesis. Let us move to that. Let's start with the state of the art. The origin of this problem traces back to Boole's seminal work, which was subsequently pursued with a focus on decidability by Skolem. The problem of Boolean function synthesis have always been a great interest of both theoreticians and practitioners, and over the decade, we have seen a significant improvement on both the prospect. Theoretically, Akshay et al. In 2018 proved that there exists a problem instance where Boolean function synthesis must take superpolynomial time under the complexity theoretic assumption P not equal to NP. On the other hand, the algorithmic approach progress for this column function synthesis has been driven by a diverse set of techniques. For example, CIGAR, the counter-example guided abstraction refinement based approaches, knowledge representation based approaches, input-output separation, and incremental determinization. Despite peak intense algorithmic development in the recent year, a large number of instances still remains beyond the reach of state-of-the-art tech. Towards the goal of having a better synthesis technique, we propose Manthan, a data-driven approach for Boolean function synthesis. Motivated by the success of machine learning, Manthan uses machine learning to come up with candidates. As we all know, the machine learning needs data. So Manthan does constraint sampling to generate the data, and the candidates are later defined using formal and automated reasoning. Hence, Manthan works at the intersection of machine learning, constraint sampling, and formal reasoning. It takes specification f of xy as an input, it generates the data, and with that data, it learns the candidate function. And later, it does a verification check on the learned candidate function. Manthan is a sound system. It will return a column function psi if and only if the candidate passes the verification check. Otherwise, they have to undergo a refinement iteration. Let us look into each component in detail.
So data generation, we have a specification f of xy in our hand, and the satisfying assignment of f of xy, that is the valuation of x and y that satisfy the specification, can be considered as data. But the problem with this approach is the number of possible satisfying assignment can be exponential in terms of cardinality of x and y. To resolve this, we can consider the data points sampled uniformly at random from the possible solution space. But the question arises here is sampling uniformly at random from the possible solution space is good enough? Let us see this through an example. So here we are considering the same specification which we considered earlier. And the table here represents all the possible satisfying assignment for this specification. As we want to capture the relation between input and output variables, we can have a different valuation of y1, that is the output variable, for the same valuation of x1 and x2, that is the input variable. That's where it differs from the classical machine learning. In the classical machine learning, we should have exactly one label for the output variables for the same valuation of input variables. And if we ask to sample 4 data points uniformly at random from this possible solution space, we may get the table on the right hand side as our data points. And as we have already discussed, for this particular specification, we may have different possible Skolem function, which includes a constant function 1. But with these data points, machine learning approach will not be able to learn a simpler Skolem function. If we can somehow sample 4 data points like this, notice the change here. For all the valuation of x1 and x2, y1 is 1. Now with this data, the machine learning will be able to learn a simpler Skolem function. One may think that, okay, we need to bias the value of output variables towards 1 to generate this data from the possible solution space. But that is not the case. Let us consider another example. So here we have just negated the variables in the specification. And this table here represents the satisfying assignment for this specification. Similar to the previous example, this specification also have many possible Skolem functions. That includes this constant Skolem function 0. And if we ask to sample 4 data points uniformly at random, we will get this right-hand side tables or the data points. And the machine learning algorithm will not be able to learn a good or a simpler Skolem function. But if we can somehow be able to get this as a data, notice the change again. We have for all the valuation of x1 and x2, we have y1 as 0. So if we can gather somehow this data, it will be easy for machine learning approach to learn a simpler Skolem function. So here we are hypothesizing that just sampling uniformly at random is not good enough to learn a function from a relational data. And towards this end, Manthan proposes a weighted sampling strategy that samples uniformly over x variables and biases over the y values. So the reason to sample uniformly over x is to cover the whole domain of the input variable. So first is try to sample small fraction of data with biasing y towards 1 and biasing y towards 0. And with those data, it tries to learn a good bias Q for the y variables. And then later, it again samples x uniformly at random for the x variables and with bias Q for the y variables. And that's how Manthan generates the data from a specification to learn a candidate Skolem function. So the next is, how do we learn the candidate Skolem?
So let's look back. Let's consider the same running example. And let us assume that this is the data we get from the data generation phase. So if we just look into the valuation of y1, we can say that it's a binary classification problem where we want to learn the output variable y1 in terms of x1 and x2. So we can consider the valuation of x1 and x2 as a feature set and the valuation of y1 as a label, and we can learn decision tree to represent y1 in terms of x1 and x2. So with this data, we can learn the decision tree. So when x2 is 1, so red line represents here x2 being 1. So we can see that when x2 is 1, y1 is also 1. And when x2 is 0, so this green line represents here x2 being 0. There is no direct classification for y1. So we have to look into the valuation of x1. And we say that when x2 is 0 and x1 is 1, we have the y as 0. And when x2 is 0 and x1 is also 0, we have the y value as 1. So this is the decision tree we can learn from this data. And to come up with a candidate function, we can consider all the paths with the leaf node 1. So here is, for this path, x2 is 1. So we say that x2. And for this path, x2 is 0 and x1 is also 0. So we can disjunct it with this path. So when x2 is 0 and x1 is 1. x1 is also 0. So this is the candidate function we get. Let us try to generalize this. To learn a candidate function psi I, we can consider the valuation of x, the input variables, as a feature set, the valuation of yi as a label, and with this feature and label set, we can learn the decision tree classifier. And the candidate function psi I is nothing but the disjunction of all the paths with tree, all the parts of the tree with leaf node 1. And that's how Manthan generates a candidate function. So now we have the candidate function. The next step for Manthan is to verify whether the candidate function is this Skolem function or not. To do so, Manthan constructs a formula E over the variables x, y, and y prime. We call this formula E as an error formula. Look into this particular clause of error formula where we have the same x, but y is different. So we have in this particular clause, in the specification, we have y, and here we have y prime. And the value of y prime is fixed as the output of Skolem function. For a particular valuation of x, y prime will take the value outputted by the Skolem, outputted by the candidate functions. So let's further analyze this error formula. So if there exists a valuation of x such that f of xy evaluates to true and f of xy prime evaluates to false. Remember, y prime needs to take the value same as the output of candidate function. So for evaluation of x, if f of xy evaluates to true and f of xy prime evaluates to false, then this negation here makes sure that the error formula is set. And similarly, if for all the valuation of x, where f of xy evaluates to true, f of xy prime also evaluates to true, then the negation here will make sure this error formula is unset. So as a verification check, Manthan checks the satisfiability of this error formula. If the error formula is unset, then Manthan returns the Skolem function psi. And if the formula is set, we have a counterexample sigma, which is a satisfying assignment of error formula to fix. If the candidate function is not able to pass the verification check, that is, the error formula turns out to be set, the candidate needs to undergo a refinement iteration. But the question arises is, out of m Skolem function, which one of those we need to refine? So we have to find the potential candidates to refine. So here we have the error formula as set and sigma is the counterexample. And we know that as the error formula is set, with the current counterexample, f of xy is evaluating to true and f of xy prime is evaluates to false. Potential candidates to refine can be the functions corresponding to yi, where the sigma yi is not same as sigma yi prime.
Let psi be the candidate function that Manthan decided to refine. As we know that with the current valuation of x, the f of xy is evaluating to false. The aim of our refinement iteration is to make f of xy evaluates to true with the current valuation of x. So if with the current valuation of x, psi I is giving us the output 0, we want it to give us the output 1. Similarly, if it is giving us the output 1, we want it to give the output 0 after the refinement. So how do we do that? So for that, Manthan constructs a refinement formula called beta. So the specialty of beta formula is it is always true with respect to the current valuation of counterexample. It is nothing but the conjunction of literals of x according to the counterexample sigma. That is, let's say we have sigma of x1 equal to 0, that is the valuation of x1 in the counterexample sigma is 0 and the sigma of x2 is 1. The corresponding beta formula will have negation of x1 and x2. So that's how Manthan constructs a refinement formula beta. And if the output of the psi function is 0 before the refinement, it disjunct the beta formula with the current candidate function to refine it so that it gives us the output 1 after the refinement. Similarly, if the output of the current candidate function is 1, it conjunct it with the negation of the beta so that the candidate function psi gives us the output 0 with the current valuation of x. That's how Manthan refines a candidate function and it synthesizes the Skolem function. Let us move to the experimental evaluation section. So we compared Manthan with the 3 state-of-the-art tools, CADIT, DFSS and C2SIN over 609 publicly available benchmarks from different domains within a timeout of 7200 seconds, that is 2 hours. The objective of our experimental evaluation was twofold.
To see the impact of data, that is the quality of the samples produced, and the second, to compare the performance of Manthan with respect to the state-of-the-art tools. So let us first discuss the impact of different sampling schemes and the quality of samplers. The first column here represents the different sampling strategy. So CryptoMiniSat here is the state-of-the-art set solver, and we consider the naive enumeration of satisfying assignment as our samples. That is the iterative enumeration of satisfying assignment, one after the other as a samples. The second is uniform sampler. So we just samples uniformly at random for both x and y variables. And the third is weighted sampler. In this strategy, we uses the adaptive edit strategy that we have discussed in the data generation component of Manthan. So column 2 represents the instances solved with the zero refinement, that is where the candidate functions learned by the machine learning is this column function, and they did not need to go any refinement iteration. They passes the verification check at the first step. And the third column represents the total instances solved. As we can see from the second and third row of this table that we need to sample from the possible solution space. Just the naive enumeration of satisfying assignment is not good enough.
Second and third row of this table proves our hypothesis that just sampling uniformly at random is not good enough. We need to sample smartly to learn a function from a relation. Let us move to the performance evaluation of Manthan. So the plot here is a cactus plot with the y-axis being the CPU time and the x-axis being the instances solved. And a point xy represents that x many instances are solved by a solver in y much time. So as we can see here, Manthan improves over 76 benchmarks over the state-of-the-art tools. Not just that, it is able to solve 60 more new benchmarks that none of the state-of-the-art tool is able to solve. These 60 benchmarks are just solved by Manthan. Manthan not only just performing good over the experimental evaluation, it also opens up several interesting questions like what is the ideal distribution to generate the data? We have proved that the just sampling uniformly at random is not good enough, but we still don't know the answer to the question, what is the ideal distribution to sample? We have observed that the candidates learned by machine learning are good enough, but still we don't have any quantitative measure to measure the goodness of the candidate functions. And can we use this kind of techniques to do the program synthesis, program repair and all? So with this, I would like to conclude my talk. So we have discussed about Manthan, a data-driven approach for Boolean function synthesis. Manthan uses constraint sampling to generate the data, and with the data generated, it learns the candidate using machine learning approaches, and the candidates are later refined using formal and automated reasoning. With this approach, Manthan is able to solve 60 new benchmarks that none of the state-of-the-art was able to solve, and it opens up several interesting questions. The tool is available online. Please give it a try. Thank you.